You know, for decades, we've all seen it, that iconic image of a starship just streaking across the galaxy, literally bending space. Star Trek's warp drive. It's more than just sci-fi tech. It's become this symbol of humanity's ultimate dream for exploration. But is there any real science to it, or is it just a beautiful fantasy? Well, let's break it down.
We're going to dive into the absolutely monumental engineering hurdles and the, frankly, mind-bending physics that are standing between us and the stars. Is it actually possible for us to bend the cosmos to our will? Or are we talking about something that's just fundamentally impossible? I mean, here's the core of the problem, right? It's distance. The universe is just staggeringly huge. Our very nearest star, Proxima Centauri, is over 4 light years away. To put that in perspective, with the fastest thing we have right now, that trip would take tens of thousands of years. So yeah, to really become a galactic species, we need a completely new rulebook. And that's exactly where we shift from pure fiction to some really fascinating, though you'll see, incredibly challenging science. It turns out there is a theoretical concept that gives us just a little glimmer of hope for faster-than-light travel. So get this. Back in 1994, a physicist named Miguel Alcubierre came up with this wild idea. He thought, what if instead of trying to move a ship at impossible speeds through space, you could actually move space itself around the ship? And that, in a nutshell, is the Alcubierre Drive. The whole approach is just fundamentally different. A normal rocket pushes something through space, right? But the Alcubierre Drive would create what's called a warp bubble. It would actually squish space-time in front of the ship and expand it out behind. The ship just sits there, protected inside this bubble, basically surfing a wave of space-time. And here's the kicker. Because it's space itself that's moving, the universe's ultimate speed limit, the speed of light, doesn't apply. Sounds amazing, doesn't it? Okay, but here comes the first absolutely enormous catch. To create that space-time wave, you need a very, very special and, well, problematic ingredient. And this really gets to the heart of the paradox here. The math kind of works out on paper, but only, and this is a big only, if you can get your hands on some material with properties that seem to break the known laws of nature. So this crucial ingredient is called exotic matter. See, everything we know, from a grain of sand to a giant star, has positive mass and creates gravity. It pulls things in. But to bend spacetime the way this drive needs, you'd need matter with negative energy density. Think of it as anti-gravity. It would literally push space apart. And the problem with that? We've never seen it, we've never made it, and it might not even be possible for it to exist. It's a pretty big roadblock. Okay, but let's just play a game for a second. Let's pretend we solve that. We find some exotic matter under a rock somewhere. Well, then we run headfirst into the next impossible hurdle, the power requirement. We are talking about an energy bill of cosmic proportions. Yeah, the first calculations were just mind-blowing. The energy needed wasn't what Jupiter produces in a year. It was the energy you would get if you could convert the entire planet Jupiter into pure energy, thanks to Einstein's E=mc². Now, newer theories have brought that number down a bit, but the amount of power we're talking about is still way, way beyond anything our civilization could even dream of producing. And just to put that scale into perspective, it's almost funny. If the energy needed for a warp drive is a giant skyscraper, then the total amount of energy that all of humanity uses in an entire year, it's like a single brick on the sidewalk. We're not even in the same ballpark. It's not even the same sport. And, you know, as if all that wasn't enough, there are other, less than ideal side effects. The intense space-time bending could create tidal forces that would just shred the ship and everyone in it. The front of the warp bubble would cook up a storm of lethal radiation. Oh, and when you arrived at your destination and turned the drive off, the bubble's collapse would unleash a blast of high-energy particles that would probably sterilize the entire planet. So, not the friendliest way to say hello. So, okay, after all that, where does this leave us? We've got this beautiful theory, this glimmer of a possibility, but it's buried under a mountain of what seems like impossible physics and unbelievable engineering challenges. And that really shows you the gap between the dream and where we are today. The sci-fi dream is warp speed, near instantaneous travel. Our scientific reality? Well, we're focused on things that are a lot more plausible, if a lot slower, like powerful fusion rockets or giant generation ships that would take centuries to reach even the nearest stars. The verdict, based on everything we understand about the universe right now, is pretty clear. The Alcubierre Drive is an amazing, brilliant piece of theoretical physics.
But the practical challenges, from having to invent non-existent matter to somehow harnessing the energy of an entire planet, they put it firmly in the category of science fiction, at least for now. And that leaves us with one final fascinating question. Are these hurdles truly impossible, or are they just impossible for us right now? Could some future breakthrough, some new understanding of physics show us a shortcut? Could there be a way to make exotic matter or to bend spacetime without needing a gas giant in your fuel tank? For now, the stars are still very, very far away, but that dream of reaching them, well, that's what keeps pushing us forward.